Assignment 9, 2.2, Graphical and Algebraic approaches to the definition of limits. I will apologize in advance. I am sick, so my voice sounds horrible. So sorry about that. All right, on to our essential question. Given a function f, how do you decide whether f of x has a limit, we'll call the limit L, as x approaches C? Okay, and I'm going to start with the definition of a limit. This is a formal definition of limit. Okay. So I'm going to do a little bit of, I'm getting this from page 34. Okay. So we can say that L is equal to the limit as x approaches C of f of x if and only if the following things are true. So for any real number epsilon greater than 0, no matter how small, comma, I'm going to kind of pull out the important pieces here. I'll do bullets. Okay, for any real number epsilon greater than 0, no matter how small, there is a number delta also greater than 0 such that if x is kept within delta units C, but not equal to C, so but x does not equal C, then f of x stays within epsilon units of L. That's your formal definition of a limit. Now let's draw a picture of what the heck it is we're talking about here. So we have some function, and it looks like this. We'll put a hole in there, something like that. Okay, so this is our function. So that this is my x-axis, This is my f of x. Now we're going to say that c is here. Okay, so this is the area that I care about. I'm asking myself, what's the limit of this function as x approaches c? Now don't forget that limit has everything to do with as x approaches c from both the left and from the right. Okay, even though that's not in this definition, that's important. Okay, and so here's L in my limit. What this is saying is that for any real number epsilon that's not 0, okay, so it doesn't matter how small it is, but basically I need to keep within a certain amount of units of this limit, okay? So somewhere in between maybe these two parts, okay? So I'm going to draw. And how about if I use some color here? So if I'm epsilon units above my limit, then that means that I'm going to be delta units to the right of my c value. And if I'm epsilon units below my actual output, we're going to call the limit, then that might mean that I'm delta units to the left of c. So that's all it's saying, is that if you are basically on this graph and you're coming from the left towards c or from the right towards c, then basically you're also going to be approaching this limit from both basically the top or the bottom, depending on if you're coming from the left or from the right. Now, there's a whole bunch that your book does with this epsilon delta. It's quite complex, and I've chosen to cut a lot of it out because I've heard that most of it's not on the AP exam. So we're not going to do too much with this, but we are going to explore limits quite a bit, okay? Just not with this epsilon delta notation. Okay, so with that, let's look at page 37. Let's go ahead and look at numbers 4 through 12 even. Okay, let's just look at those and let's determine if we have a good understanding of what limit means. Okay, so I'm going to move my paper here. So for number 4, okay, let's read what we're supposed to do. For problems 3 through 12, state whether the function has a limit as x approaches c. If so, tell what the limit equals. Alright, so as x approaches c from both the right, this is the left, from the left and from the right, what is my y value approaching? Right, so as I come at it from the left, I'm up here somewhere, and so that means I'm coming down on my limit. As I come at c from the right, I'm down here somewhere, which means I'm coming towards the limit from the bottom. Okay, so yes, they both approach. As I'm coming from the left and the right, I am in fact approaching one output. What does that output seem to be? It looks to me like it's 2. Okay, so we can say that the limit there is 2. So we'll say for number 4, so yes, limit equals 2. Alright, let's try 6. Where's 6? There we go. Alright, so let's look at our function. Let's look at our c value on the x-axis. As we approach from the left and as we approach from the right, what does it appear our function is doing? So as I approach from the left, I'm a little bit before or below, right? But I'm getting closer and closer to some value here. And as I approach from the right, I'm a little bit above, but I'm coming closer and closer and closer to this limit L. Well, what is it? That limit appears to be 5. Now, it's actually not defined at C. This function is not defined at C here, but it is defined at C here. So the actual value, f of C, the actual output is 8, but that has nothing to do with the limit. The limit says if I look at this function and as I approach C from the left and the right, then I need to be approaching my output value that is the same. And that happens here. We're approaching 5 from both the top and the bottom. Okay, so I'm going to say yes. My limit is 5. All right, let's look at 8. Okay, so 8, here's my C. Okay, I'm looking from approaching C from the left. When I do that, I'm up here, right, and I'm coming down towards this value. Okay, and now I'm also approaching from the right, and when I do that, as I approach from the right, I'm approaching this higher value. So is there a limit? Is there one output that both, if I approach C from the left and the right, that I'm approaching on my y-axis? It doesn't appear like it, right? When I approach from the left, looks like I'm approaching 5 for my output. When I approach from the right, looks like I'm approaching 12 for my output. So there is no limit. So for 8, we're going to say no. We'll do 10 next. So how about 10? What do you think? Well, again, looking at C, as I approach from the left, looks like my function is heading up to 20 as my output. When I approach from the right, looks like my function is heading up to 20. So yes, this one is a function. I'm sorry, this one does have a limit. That's algebra 2, sorry. Okay, this one does have a limit. And my limit happens to be 20. So maybe I should write that for all of them. That's good. And let's do 12. So 12, as I approach from the left, my function looks like it is going to negative infinity. So there's probably an asymptote right here at C. Okay? But as I approach from the right, it appears like it's heading up to 3. So as I approach C from the left and the right, am I approaching the same outputs? I am not. So therefore, there is no limit. So there are different types of discontinuity of a function. And some discontinuities will allow you to have a limit, and other discontinuities you will not be able to have a limit. Discontinuity. Alright, so let's graph a function here. We'll use this as our example to kind of guide our thoughts. So let's see it. 2. So there's one piece. The other piece will be something like that. Where here and here. Alright, so one type of discontinuity is removable discontinuity. This is what happens whenever you end up having a hole in your function. Okay, so there's removable discontinuity then. I have a hole right here. So if you remember, sometimes when we're trying to factor and simplify an equation, right? Maybe you have like x minus 3 in both the numerator and denominator, and you can factor that out. That would mean that you'd have a hole at x equals 3. Or in this case, maybe my function, in my numerator and denominator, I have a factor of x minus 1. When I reduce that, that means I still can't have x equaling 1. It's still going to be undefined there. So I'm going to have a hole there. Okay, so I've got a hole at x equals 1. That's my removable discontinuity. And basically it's called that because you can remove the discontinuity by defining f of 1 to be some number. And here I'll just say, if I said, you know what, no, I'm going to define it to be 2. I can do that. So I can remove that discontinuity. Okay? I like to think of it kind of in the opposite way. It's like, oh, the hole's been removed there, or the piece has been removed there, so I've got a hole there. And then my other type of discontinuity is step discontinuity. So it's cool that these sound exactly like what they are. So where do I have a step discontinuity? Where do you see a step here? That's going to be at this 3, right? So step discontinuity is where, as you approach 3 from the left and the right, you're getting different outputs. So that creates the step. So there's a step discontinuity at x equals 3. So basically there is a step since you approach different outputs, as you approach x from left and right. Okay, so I'm just going to do one problem with you, and I'm not really going to follow the directions, but I am going to use the equation from page 38, number 24. So we are given the fact that f of x equals 6 minus 2 times x minus 3 to the 2/3. Okay, so I want to find the limit. So I want to know the limit as x approaches 3 of f of x. That's my question here. And I want to calculate this 2 ways, okay? So I'm going to look at this. The first way, I'm going to use my table of values. And then the second way, I'm going to evaluate using algebra, so algebraically. Okay, so I want to do that 2 different ways, and I'm kind of making this up so that I can help guide you into the problems that I am going to assign you, but I don't want to do those problems. Alright, so first thing, let's use a table of values to confirm what the limit's going to be as x approaches 3 of this function. So that means you want to go into your calculator and if you haven't already, go ahead and take a minute and graph it. It's good to have a little idea of what this looks like. By this point, hopefully you guys are really good now at evaluating this graphically. Right, because you've done a few problems in pre-calculus. You're going to do a few more problems tonight in your homework, or tomorrow in your homework. So I look at this graph and I'm saying, oh look, from the left and from the right, it's approaching something. Let me go into my table to be more precise with that. I could also do a calculation and trace. But I'm going to go ahead and go into my table, and I care about at 3. And to get really precise with this, I'm going to go up and down by thousandths. So when I look at my table, I notice that as I come from the right of 3, so come from being bigger than 3, as I get closer and closer and closer to 3, it's approaching 6. Let's see if it's the same from the left side of 3. So as I come from the left side, looks to me like my outputs are getting closer and closer and closer to 6 as well. Okay? So, when they're asking you to do something like, I think you have a problem that says, do an appropriate calculation to show that such and such is the limit. An appropriate calculation might be, sometimes maybe you just need to look at a table of values. You need to see, as you get closer and closer to that value of x, maybe you need to actually figure out, hey, what are some of those outputs that go with those? Okay, so that's one way. So using a table of values, so for 1, I'm going to say that the limit as x goes to 3, as x goes to 3 of f of x equals 6. And that's because I have this table of values where I know that, so here's 3 and this is 6, but at 2.99, I had 5.98. And at 2.998, I had 5.9683. And at 3.001, again, I was at 5.98. And at 3.002, I was at 5.9683. This one happens to be symmetrical. Okay, wonderful. So now let's try and answer it the second way. So hopefully you remember this from pre-calculus, that if I'm looking at the limit as x goes to 3 of f of x, sometimes I can try to plug this limit or this x value into my function and see what happens. So that's what I'm going to do. I'm going to say, well, as we approach 3, this is going to take on the form that my input will be 3. So this becomes, let's see, 6 minus 2 times, 3 minus 3, that's 0. So this whole piece right here just becomes 0, and I'm left with 6. So that's evaluating it algebraically. Either way, the answer is 6. And then graphically is pretty obvious.